In the BNSF wheel shop in Havelock, Nebraska, a freight locomotive wheel sits on the floor before it goes back into service. It weighs 900 pounds. It is machined from a single forging of high-carbon steel, heat-treated to a hardness that takes weeks to achieve. Its diameter is roughly 42 inches, about as tall as a kitchen countertop. When it rolls on a rail, the area of contact between this 900-pound steel object and the steel rail beneath it is approximately the size of a dime, not a coin balanced on edge, a dime lying flat, about 1 square centimeter. Through that 1 square centimeter, the wheel carries its share of a locomotive that weighs 200 tons, transmits the force that pulls a train of 15,000 tons, and absorbs every rail joint, every thermal expansion gap, and every imperfection in the track at whatever speed the train is running. The dime is doing all of it. And if that dime develops a crack that no inspector can see with the naked eye, the train does not slow down gradually or give the crew a warning they can act on in time. It fails, and when a wheel on a freight train fails at speed, the question is not whether the train derails, it is how many cars come with it. Here is where it starts. A 6-axle freight locomotive, like the GE AC4 400CW, runs on 6 wheel sets, 2 wheels per axle, pressed onto a steel shaft, rotating together as a unit. Each complete wheel set weighs more than 2,000 pounds. 6 of them together account for more than 6 tons of rotating steel, and that is before the truck frames, the traction motors, the fuel, or the locomotive body above them. The full locomotive weighs 213 tons. The contact patch, that 1 square centimeter per wheel, is operating under contact pressures exceeding 145,000 pounds per square inch. For comparison, a car tire operates at around 35 psi. The train wheel is running at more than 4,000 times that pressure, continuously, for hundreds of thousands of miles. That pressure exists because of the same property that makes a freight train the most efficient land transport system ever built. Steel on steel has extraordinarily low rolling resistance. A freight train consumes roughly 1 gallon of diesel to move 1 ton of cargo 500 miles. A semi-truck moves the same ton the same distance on about 7.5 gallons. That efficiency advantage comes almost entirely from the wheel-rail interface. 2 hard surfaces, minimal deformation, minimal energy lost to flexing. But low rolling resistance is inseparable from low friction. The same steel-on-steel contact that makes a train efficient to move makes it very difficult to stop. A loaded freight train at 55 miles per hour needs more than a mile of track to stop under emergency braking. That is not a brake system failure. That is physics. When the brakes clamp hard enough that the wheel stops rotating, but the train is still moving. When the wheel locks and slides, something happens to the tread surface that sets up the next category of problem. But the same property that makes a train efficient is what makes a defect in that wheel so unforgiving. When a wheel locks and slides instead of rolling, the tread surface contacts the rail at a single point for the entire duration of the slide. Steel grinding on steel at train speed removes material from that one spot. When the wheel finally starts rolling again, it has a flat section ground into its circumference. Every time that flat section comes around and contacts the rail, it strikes the rail like a hammer instead of rolling over it smoothly. Wheel impact, load detectors, wild systems. Sit beside the track and measure exactly this impact force as trains pass over them at operating speed. A wheel rolling normally might register 20,000 or 30,000 pounds of force on the rail. A wheel with a significant flat spot can register 80,000 pounds or more with each revolution. The Federal Railroad Administration and the Association of American Railroads use wild data to flag wheels that need to be pulled from service before the hammering damages the track or causes a more serious failure. In March 2015, a BNSF crude oil unit train near Galena, Illinois, derailed and caught fire. The NTSB investigation found that a wheel had developed subsurface fatigue cracking. In the months before the derailment, Wild detectors had recorded impact loads for that wheel near or above 80,000 pounds on 4 separate occasions. The wheel was not removed. On the 5th occasion, the wheel did not produce an impact load reading. It produced a derailment. A flat spot is visible to a trained inspector who knows what to look for. What kills trains is not always visible. The deeper problem with freight locomotive wheels is not what happens on the surface. It is what happens inside the steel, in the zone that no visual inspection can reach. Steel under repeated cyclic loading develops microscopic cracks at points of stress concentration. These cracks grow incrementally with each load cycle. Each revolution of the wheel under load, each thermal expansion and contraction, each imperfection in the rail surface that sends a shock through the steel. The cracks propagate from the inside out, parallel to the tread surface at first, then turning perpendicular and extending toward the outer surface. The wheel looks normal on the outside. It sounds normal. It measures within tolerance on standard inspection equipment, and then it does not. On June 3, 1998, an ICA high-speed train in Eschede, Germany, was traveling at 125 miles per hour when a wheel fractured. The wheel in question used a design called a bandage wheel, a steel tire pressed onto a resilient rubber ring mounted on the wheel center. Intended to reduce cabin noise, a fatigue crack in the tire had been growing for months. Ultrasonic testing had failed to find it. When the tire failed at speed, the wheel derailed one car, which struck a bridge support at 125 miles per hour and brought the bridge down onto the train. 101 people were killed. It remains the deadliest rail accident in German history. On January 7, 2014, a CN freight train near Plaster, New Brunswick, Canada, derailed when a wheel on the 13th car broke from subsurface fatigue caused by a large area of porosity inside the steel. The porosity had not been detected during the wheel's original ultrasonic testing in 1991, nor when the wheel was reprofiled and re-inspected in 2006. The derailment spilled 230,000 liters of crude oil and started a fire that destroyed more than 100 meters of track and forced the evacuation of 150 residents. Eschede was Germany in 1998. Plaster was Canada in 2014. Different countries, different wheel designs, different railroads, different decades. The same technology failed to find the same category of defect both times. Ultrasonic testing works. It does not always work well enough. This is the thing nobody tells you about inspecting a train wheel. If you are finding this useful, hit subscribe. We cover stories like this every week. The inspection system for freight wheels in North America operates on 2 levels. The first is Wayside, automated detectors embedded beside the track that measure what is happening to every wheel on every train that passes over them at operating speed. Wild systems measure impact loads. Hot bearing detectors measure axle temperature. Truck performance detectors measure lateral and vertical forces that indicate misaligned or hunting wheel sets. These systems run continuously, require no crew to operate, and flag anomalies to dispatchers who can order the train to stop and inspect. The second level is workshop inspection. When a wheel is pulled from service for scheduled truing, a flag detector reading, or a visual defect, it goes into a wheel shop where technicians run ultrasonic testing equipment across it. Ultrasonic inspection transmits high-frequency sound waves through the steel and measures the echoes. A crack or void inside the steel reflects sound differently than solid material. The inspector reads the echo pattern and determines whether the wheel is within tolerance or must be condemned. The limitation is geometry. Ultrasonic testing works best when the sound wave strikes the defect at a perpendicular angle. A crack oriented at an unfavorable angle relative to the transducer may not produce a clear reflection. A crack that has grown into a complex shape, branching, turning, may produce ambiguous echoes. The Plaster rock wheel passed 2 ultrasonic inspections over 23 years. The Galena wheel generated 4 near-threshold wild readings before it failed. The inspection system that exists today is the direct result of accidents that demonstrated where the previous version of the system fell short. The inspection system that exists today is the direct result of the accidents that happened before it. On February 3, 2023, Norfolk Southern Train 32N was rolling east through Ohio when the L1 bearing on the 23rd car in the consist overheated. The NTSB's final investigation determined that the bearing failure caused the axle to separate, derailing the train. The wheel bearing and the wheel are part of the same assembly, the wheel set. When the bearing fails, the axle that connects the 2 wheels on that pair can separate from the truck frame. When the axle separates at speed, the wheel set no longer guides the car along the rail. The car derails, and in a train of 149 cars moving at operating speed, what happens to the 23rd car does not stay with the 23rd car. Wayside hot bearing detectors had registered a temperature on that bearing at 103 degrees above ambient in Salem, Ohio, 19 miles before the derailment. Under Norfolk Southern's policy at the time, that reading was classified as non-critical. The train continued. By the time the bearing reached 253 degrees above ambient at the East Palestine detector, the crew received a critical alarm and began emergency braking. The derailment had already begun. After the investigation, the Association of American Railroads lowered the threshold at which a hot bearing requires mandatory train stop and inspection from 200 degrees above ambient to 170 degrees. 19 miles earlier, a 170-degree threshold would have stopped that train in Salem. The wheel did not fail because nobody was watching. It failed because the threshold for when watching becomes action was set too high. Back to the wheel shop in Havelock. The 900-pound wheel sitting on the floor is about to be pressed back onto an axle, installed in a truck frame, and placed under a locomotive that will pull it for the next several 100,000 miles. Before it goes back into service, a technician runs an ultrasonic probe across its surface, watching the echo pattern on a screen for anything that does not belong. A car tire has a contact patch roughly the size of your palm, 4 of them, 1 per wheel. When the tire wears out, you replace it. Average life, 50,000 miles. The tire is designed to be a consumable. The wheel is not. A freight locomotive wheel is designed to last the life of the locomotive. Decades of service, hundreds of thousands of miles, under loads that would destroy any rubber tire ever manufactured. There is no soft material between the steel and the rail. There is only the contact patch, the size of a dime, doing the same job every time the wheel comes around. The engineers who designed these wheels understood the physics. They understood that low rolling resistance required hard surfaces, and that hard surfaces under cyclic load develop fatigue cracks. They built inspection systems to find those cracks in Wayside detectors to catch the consequences of the ones inspections missed, and they lowered the thresholds after the accidents showed where the line had been drawn too conservatively. That 900-pound wheel is insane, not because it is exotic or complicated. It is insane because of what it has to do, across what distance, at what loads, and how thin the margin is between the wheel doing its job and the train leaving the track. A dime's worth of contact. Everything else follows from that. Subscribe for more engineering stories that reveal the logic beneath the surface.